So my goal with this video is to thoroughly go through the most commonly taught material in semester 1 of Algebra 1, sometimes called Part 1 or Semester 1. But let's just dig into it and not waste any time. So starting with integer arithmetic, this is sort of a review from pre-algebra, but two positives. If you combine two positives, you've got lots of positives, so we get positive 8. Now, what if we combine a negative and a positive? If we add a negative and a positive, this is what I like to call a who wins by how much game. You see how we have 6 positives out on the field and then in walk 2 negatives? So we got 2 teams playing against one another, some of them positive, some of them negative. Who wins? The positives have more on their team by 4. Here I wrote things a little differently. I put the negative in a parenthesis, but we're still adding a positive and a negative, and this is a who wins by how much game. So this time the negatives have more on their team, and they win by 1. So the answer is -1. Now in this fourth question, you see how we have some negatives, and then we're combining more negatives. Now that doesn't make a positive. You're confusing things with multiplication if you accidentally think that. So if you have lots of negatives and you combine them all, you're going to have lots of negatives. We have -4. You can think about it as movement to the left on the number line. It's all to the left. Now this next example looks like subtraction, but I would encourage you to think about this not as subtraction, but think of it as 2 plus -6. There's no such thing as subtraction. Just think of it as a -6, and then you can play the who wins by how much game. So the negatives win by 4. Now in this example here, we have lots of negatives, right? Again, no such thing as subtraction. So it's really -2 plus -4. Boy, that's a lot of negatives, right? -6. On the last example on this page, we have lots of negatives. In fact, we have this double negative. So that causes it to become a positive. -1 plus +4, which of course, who wins by how much? The positives win by 3. So whenever you have a double negative, don't forget it becomes a one giant positive sign. And then you can just play the who wins by how much game. More review from pre-algebra. Integer arithmetic is so important, so I wanted to make sure I gave you a few slides on this. So +3 times +5. So a positive times a positive is always a positive. So the answer is 15. Now, what about a negative times a positive? Well, a negative times a positive is always a negative because you can think about it as 6 groups of -2. That's a lot of negatives, right? 6 groups of -2 would be -12. And the next problem, 4 times -5. Once again, a positive times a negative is a -20. -20. And then in this fourth example, a negative times a negative does give you a positive. They cancel each other out. You get a net positive. Now look at this fifth example. What if we string together 3 negatives? So that's an odd number. It's an odd number of negatives. So that causes the final answer to be negative. So whenever you have an odd number of factors all lined up like they are here, your sign is going to be negative. And then the answer, of course, is 2 times 3 is 6. 6 times 4 is 24. So one of the mottos I use with my students is sign first, number later. You see how I found the sign of the answer, and then I just took my 2 times 3 times 4 and got my 24. Now division, fractions are really division problems, right? So down at the bottom of this slide, we see -8 divided by 2. That would be -4 because a negative divided by positive is a negative. What happens when you take a negative divided by a negative? -6 divided by -2? That's +3, +3. And then 9 divided by -3, again, we have one positive, one negative being divided, so that is a negative answer, and it would be 9 divided by 3 is 3. So sign first, number later is a great motto to use. In Algebra 1 and Algebra 2, you'll be using exponents a whole heck of a lot, so let's not forget what it means to have one of those little numbers called the exponent. First of all, the 2 here is called the exponent, and the 5 is called the base. Don't forget that. The 5 is called the base. The entire thing is called a power. Now, what does it mean when you have an exponent? This means you have 2 factors of 5, and the word factor means that they're multiplying together. So 5 times 5 is the same thing as 5 squared. So the answer is not 10. The answer is 25. So 5 squared is 25. Now, 3 to the 4th is not 12. it means behind the scenes we've got 3 times 3 times 3 going on, and that's 9 times 9, which is 81, or 27 times 3, however you want to think about it. You're going to get 81. So x to the third is the same thing as x times x times x. All right, and there's no way to simplify that here. I just wanted to show that that's what x to the third means. So what does 6x squared mean? This would be 6x times 6x. So we get 36. And then what about the x? We have x times x. So I'm not going to write x times x here. What would be a better way to write that? How about just x squared? That would make a lot more sense. So just write it as x squared. Okay, so you've already seen me use some variables. Variables are letters or symbols that represent like a generic number. So they play this game called algebra the same as numbers do. So algebraic expressions are where you mix these constants, these variables, and operations like add, subtract, multiply, and divide, and exponents, and all those things. So you see 4 different expressions here: 5x, 2x plus 1, 5x squared, and x squared minus 5x. These are called expressions. And sometimes we can simplify them, and that's what we're looking at down below here. To simplify means combine or work out anything you possibly can. And if you look at this first example, I see some x's here and here. Think of that as like baskets. Like we don't know what's in the basket. It's some mystery amount. Call it x. Well, I've got 5 baskets and 3 baskets, so those combine. It's called combining like terms into 8 baskets. Again, we don't know what's in the basket, but we know there's 8 of them. And then there's this 3x squared thing. That's an entirely different type of basket. Maybe it's a box, entirely different shape. So these 2 terms are not like terms, so that's our answer. We just put a box around that and call that our answer. They are not like terms. Please don't write 11x to the third. That makes your algebra teacher very sad when you do that. So please don't do that. All right, looking at this next example, we have some like terms. Again, we've got some x terms here, and we have some plain old numbers. So let's combine everything we can. Let's start with the x's. We usually write the x's first. So positive 2 and negative 5. We're talking about x's here, so how many do we have? Well, who wins by how much? The negatives by 3. So when we combine them, we get negative 3x. Now, the 6 and the negative 3, those combine to be positive 3. So our final answer would be negative 3x plus 3, or 3 minus 3x. Either way you want to write it, you can switch things around, no troubles. In algebra, we're going to work a lot with variables. So variables are letters that play this game like numbers do, so we have to remember about order of operations. Some students like to learn PEMDAS. PEMDAS is a way to remember order of operations. You always do the parentheses first, and then you do the exponents, and then you do any blocks of multiplication and division left to right. And then at the very end, you add and subtract anything you can. Now, I like to say there's no such thing as subtraction, so I'm just adding all the positives and negatives up at the end. So let's look at 5 times 2 plus 1. Is there any parentheses? No. Any exponents? No. But is there some multiplication and division? Yes. There it is. 5 times 2. We do that as a block left to right. So this is 10. 10 plus 1 is 11. So the very last thing we do is the adding and subtracting. So we got 11. What about this next example? You see how I'm squaring the 2 now, right? Whenever you see an exponent, ask yourself, what is the base? The only thing being squared here is the 2. So PEMDAS says that we do the exponents before the multiplying. So we get 4. Right there in the middle is 4. And then the 5 and the 1 wait for phase 2 here, or step 2. Now in step 2, we're going to multiply. So this gives you 20. 20 plus 1 equals 21. So the answer to that second one is 21. Now on this third one, I put some parentheses there. So those are grouping symbols. So we jump inside the parenthesis. 5 times 2 is 10. Okay, and then the next step would be, okay, we're done doing parentheses, so are there any exponents? Yes, and what is the base there? A 10. So 10 squared is 100. 100 plus 1 is 101. So that would be the answer to the third one. Okay, let's go down below now. What about 5 plus 8 divided by 2 times 4 minus 1. What a mess, right? So you look for any exponents. No exponents, no parentheses. Okay. Multiplication and division as one big block left to right. So you cannot take 2 times 4 and get 8 first. I know it's really tempting, right? You look at this and you think, oh, that's 8. Well, I'm sorry, but you're going to get the wrong answer if you do that. You got to do 8 divided by 2 first. So this has to go first because we're going to go left to right here. So this is 4 times 4, which is 16. So that entire blue block there in the middle came out to be 16 because it's 8 divided by 2 is 4, and then you take the 4 times the 4. Then you combine all the positives and negatives. 21 minus 1 would be 20. All right, we've got a lot going on this screen, and on this particular problem, there's quite a bit here. So let's jump inside the parentheses. Now, these brackets are also grouping symbols. They're the same thing as parentheses. It just looks a little nicer if you do brackets. It's easier to keep track of what's going on. So if you parachute yourself deep inside the parentheses, you will land right here, right? 3 minus 1 is 2. So inside the parenthesis, we have a 2, and that's going to be the base that's going to need to be squared, right? So we have 2 times 2 minus 4 all inside the bracket. I'm changing it to a parenthesis now simply because we don't need the bracket anymore. Now we do any exponents. 3 times 4 minus 2 times 4 minus 9. Now we still have parentheses, right? So we're still working inside that parentheses separately, I guess I should have said. So that 2 times 4 is the next thing we have to do right there, and that's going to be 8. So inside the parenthesis, we have 4 minus 8, and then we have minus 9. So that is 3 times negative 4 minus 9, right? Inside here, we get negative 4, and that will be negative 12 minus 9 is negative 21, negative 21. I've got some really important questions for you to look at. So this is something that I quiz my students on this, like every quiz for first semester, where I just keep asking it over and over in hopes that they will catch on and get all 4 of these right. Now 3 squared, that's not hard, right? That's just 3 times 3. That's not 6, it's 9, right? 3 times 3 is 9. Now, written with the parenthesis, that's no different. That just means that we have a positive 3 very clearly inside that as the base, and 3 squared, it's still 9. And what about when you square this next one? What is the base here? Well, because I put parentheses, it's pretty clear that the base is negative 3. So what is negative 3 times itself? That's just positive 9. So we still get positive 9. So all 3 of these so far have been positive 9. Well, what about the 4th one? See, this is the tricky one. This is the one that messes up students. So I wanted you to see this. This minus sign is not part of the base because this is really the opposite of 3 squared. The opposite of 3 squared because there's no parenthesis. This is really negative 1 times 3 squared. So this is negative 1 times 9, which is negative 9. Negative 9. So this is one that trips up students. So I really try to drill it in my students' heads and just keep quizzing them on it. So hopefully that makes sense to you. Just think that that minus sign is not part of the base. We're only squaring this guy because there's no parenthesis. Everyone across the world just agrees that this is going to be the opposite of 3 squared. We all have to come to the same agreement, right, on how we do these problems. That's what order of operations does for us, where we all can calculate and get the same answer when we work a problem out like these. Next up is a thing called the distributive property. So on this first example, you see how I have just numbers. Just numbers. Now normally with PEMDAS, you would jump inside the parenthesis and you'd say that that is 6, 5 times 6, and then of course that comes out to be 30, right? Well, there's another way to get the answer. There's another way to get 30, and what you can do is distribute. That means multiply the 5 against the 2. That gives you 10. And then you can also take the 5 times the positive 4, and you get positive 20. So what happens when you combine those two? you get 30. Oh my goodness. And see how these are the same answer. So either way is correct. Either way is correct. And I'm showing this with numbers so that you can do the same process with variables. So we can take this number that's out front, 5, and we can multiply it into this parenthesis. So we would get 10 times x for the first multiplication problem. And then the second multiplication problem is here. Now we have a positive times a negative. You remember what happens there? We get a negative 15. And that cannot be simplified. Those are not like terms. We've got a basket, and then we have some apples or whatever these are outside of a basket. So this cannot be simplified to negative 5x or anything else, all right? That is the answer right there. Okay, looking at the third problem in the bottom left here, this time I put a negative number out front, but no worries. All we do is follow the same process. We multiply that in, and we get negative 6x, and then the second arrow is going to be a negative times a negative. Remember, no such thing as subtraction. Don't think about that as subtract 5. Just a negative 2 times a negative 5 is positive 10. Positive 10. Okay, the fourth problem. Boy, it's so tempting, isn't it, to write 6 minus 5. You look at that and you think 6 minus 5. Well, that's 1. So the answer is x plus 2. But don't forget about order of operations, PEMDAS. You have to do anything inside the parenthesis first. Okay, there's nothing we can do inside the parenthesis because we have an x and a 2. But when you do the multiplication and division blocks, it's these guys right here. So we're going to take our negative 5 and multiply it in. And we get negative 5x minus 10. Now, the number 6 is just chilling here for the step 2. So now we combine our like terms. We have a negative 10 and a positive 6. So who wins by how much? Because we're just combining them. The negatives win by 4, and then we have a negative 5x also in the problem. So that's one way to write it. Or you could write negative 5x minus 4. Solving one-step equations. Now, in order to solve an equation, you're trying to figure out what's called the solution. And the solution is a number that works. The number that works. So on the second one, for example, what minus 8 is 2? Well, the answer is 10, right? We know that 10 minus 8 is 2. So we're looking for the number that works if you were to substitute it in, if you were to plug it in. But there's also these inverse operations. We like to show our step on equations so that, when the equations get difficult, as you know that they do, we want to have a process to fall back on. So on this first question on the left side here, we want to get rid of the positive 5. I like to think about it as getting rid of. So if we want to get the x by itself, we need to get rid of the positive 5. So what's it going to take? Let's place a negative 5 there, or if you want to think about it as subtraction, that's fine. I like to think about it as placing a negative, because then when your brain is processing this right side, you are combining two negatives. There's no such thing as subtraction. They're just negatives, all right? And it's a lot easier to think that way, in my opinion. So negative 6 would be the answer. X is negative 6. And then you can check by plugging in right there. So negative 6 plus 5, does that question mark, does that equal negative 1? Negative 1 does equal negative 1. So I've graded my own problem. I've determined that I did get it right and that is the solution. You can do that every time with an equation. All right, so on this right side, we already said the answer was 10. So how do we show our work? What is the inverse? What is the opposite of subtracting 8? Let's place a positive 8 there, right? If we place a positive 8, it will cancel the negative 8, and then x will be all by itself, which is what we want. And then on the right side, we have to do the same thing, because I didn't say this already, but we got to keep that balance. So whatever you do to one side, you have to do to the other. And if you need some more help on equations, I did make a couple of videos on basic equations and then also more advanced equations. So check those out after you finish this review video. Okay, so we get x equals 10, and we could check our work. 10 minus 8 does equal 2. What about this third question here? 3x equals 10. What do we do? Well, how is the 3 attached to the x? That is 3 times x. 3 groups of something is 10. 3 times something is 10. Now you might be thinking, wait, 3 times 3 is 9, 3 times 4 is 12. This problem is impossible, right? Well, no, we're just going to get a fraction as an answer, and sometimes that happens. So the opposite of multiplication, the inverse of multiplication, is division. And 3 divided by 3 is 1. So we end up with our fractional answer, 10/3, or if you want to write 3 1/3 or 3.33 with the 3 repeating, that's fine. I usually just leave the answer 10/3. So a lot of students freak out when they see fractions, but just think about it as division. We want to get rid of the 4. How's it attached to the x? It's attached with division. So the way to get rid of that is not by dividing by 4. We will multiply by 4 on both sides. Now I wrote it 4 over 1 for a reason you'll see here next. So I'm going to write multiplication times 4 on both sides. Now, whenever you have a 4 on the top and in the bottom, that's 4 divided by 4, which is 1. They cancel. So on the left side, we have achieved our goal. X is all by itself, and the answer is 32. So you could plug it in. You could check, right? 32 divided by 4, does that equal 8? Yes, it does. It sure does. So that's the answer. Okay, this last example, 3/2 x equals 6. This is one that students, again, they freak out when they see the fractions and they're worried about, well, how do I get rid of that? I certainly don't want to divide by 3/2 like that because that would be so confusing, right, if you start dividing like that. So instead, we remember how to divide fractions. We multiply by the reciprocal. That's the same thing as dividing, or some students say keep, change, flip, which is not a bad way to remember this. So we multiply by the reciprocal. So we multiply by 2/3. And then on the right side, think of that as 6 over 1, and we're going to multiply by 2/3. So on the left side, the 2's cancel, the 3's cancel. We're left with x equals, and when you multiply fractions, you do the top, right, first, and then you do the bottom, and that equals 4. So x equals 4 is the answer here. And we multiplied by the reciprocal. So make sure you take a close look at that, store that deep in your brain, and do not forget that you can multiply by the reciprocal to get rid of a fractional coefficient, which is what that's called. Multi-step equations, we will be doing our order of operations, our PEMDAS, in reverse. So we always look to see if we can add and subtract first. So on this first example, our goal is to get x by itself. So we really need to get rid of the 2 and get rid of the 1 at some point, right? But we have to use addition or subtraction first because we're doing PEMDAS in reverse. So what about subtracting 1? Let's just put a -1 on both sides, and we get 2x equals -4. Now we're just one step away, right? The 2 is attached by multiplication, so you cannot subtract it off of there. You have to divide it off of there. So divide by 2, x equals -2 is your answer. And if you plug it in, let's plug it in, -2. What's -2 times 2? That's -4. What's -4 plus 1? -3. You see how it works? When we plug it in, it works, so it is a solution. All right, on this next question, I put the x on the right side. I also put it in some parentheses, but no worries. We just do the distributive property. Okay, we do the distributive property, 2x minus 6 equals 10. Now, we could have divided by 2 on both sides right at the beginning, and we would have had a 5 equals x minus 3, which is a great way to do it. I usually just show students do it this way. Add 6, 16 equals 2x. You then divide by 2. You get x equals 8. X equals 8. So again, we could have divided by 2 right at the beginning, and then we would have gotten 5 equals x minus 3. Add 3 on both sides. 5 plus 3 is 8. So you get the same answer either way. Oh my goodness, look at this next one. We've got variables buried inside parentheses, and they're on both sides. So we'll be working through quite a bit in this problem. Let me ask you this. Can we take 5 minus 3 right at the beginning? Because that would be nice, right? No, we cannot. Because of order of operations, this -3 really has to be multiplied in there first. So we get 5 minus 15 plus 3x, because don't forget, a negative times a negative is a positive. Then on the right side, let's do the same thing, 4x plus 4, because we need to get rid of the parentheses. so that we can manage to get all the x's together. Right now they're on the opposite side. So let's simplify anything we can. 5 and negative 15, that's negative 10 plus 3x equals 4x plus 4. Okay, so we have x's on both sides. We do not have 7x here. Instead, let's subtract 4x from both sides. That's how we will merge them together, and we get negative 1x equals 4, because this 4 just comes down, right? We can then add 10 on both sides, and we get negative x equals 14, and then if you divide by negative 1, you get x equals negative 14. X equals negative 14. So take a close look at all my work there. We have to get the variables all to one side by removing them from one side, and then that's what merges it into the other side. This next equation is kind of crazy. We've got this fraction over here, and then we have a 2/3 x subtract 3 over here. So, you have to kind of decide what you're going to do first. There's a couple different ideas that we could do, but let me show you one trick, and I'm going to do some other equations where I use this same trick. We look at the denominators here, which are 3, 4, and 1, and we multiply everything in this problem, all three terms, by the least common multiple between 4 and 3. And the least common multiple is a 12. So if we multiply everything in the problem by 12 over 1, what happens is, watch, the 12 is canceled by the 4, leaving a 3 up there. And then 3 times 2 is 6. So we're multiplying everything by the number 12. We're allowed to do that as long as we multiply everything in the problem by the same thing. We're okay. Now on the second fraction, this 12 is canceled a bit by that 3, right? 3 goes into 12 4 times, and then 4 times 2 is 8. So we have 8, and we also have an x still. And then on the very far right here, we have minus 36. Well, look at that. I got rid of all the fractions in the problem by multiplying by the least common multiple between 4 and 3 and 1. And of course, the first multiple they have in common is 12. So that's why I multiplied everything by 12 and then I canceled. Doing the distributive property, I get 18x plus 6 equals 8x minus 36. Now I have x's on both sides. I always tell my students to deal with that first. So we've got x's here and here. So I want to get rid of one of them. So let's get rid of this one by subtracting 8x on both sides. And I get 10x plus 6 equals negative 36. I then minus 6. I subtract 6 on both sides. 10x equals negative 42. I divide by 10 on both sides. I get x equals negative 42 tenths. Now, both of those, this is a fraction that can be, both the numerator and the denominator are divisible by 2, so it's called reducing the fraction. So we get negative 21 over 5. And that would be the best way to write this answer. Or, of course, you could write negative 4 1/5. Now let's look at the concept of solving rational equations. Rational equations, well, we did this a little bit in the last problem, where we've got some fractions in the problem. Now these are called proportions. Proportions are where you have one fraction equal to one fraction. Now the fractions, of course, are different. So what you can do here is a process called cross-multiplying. Multiply. This only works when you have a single fraction equal to another single fraction. So we do what are called cross products. So we go this way, negative 3 times x is negative 3x. And then we go the other way and we get 7 times the quantity x plus 1, or 1 more than x, right? You have to put parentheses there, otherwise it's not going to work out correctly. And in the middle, we put equal. So the cross products are equal. 7x plus 7, right? When you do the distributive property, don't forget the 7 times the 1 equals negative 3x. Now, a common mistake here, I call it a mistake, would be to add 3x, because if you add 3x on both sides, then you're going to end up with 0 on the left side. So that's not my suggestion here. I would probably not do that. Instead, I would subtract 7x from both sides and get negative 10x equals 7. You then divide by negative 10, and you get x equals negative 7/10. Kind of a weird answer, but that is the answer. Okay, on the next problem, again, we're going to cross multiply. So if we do our cross product this way, we get negative 3 times the binomial, it's called because it has two terms, 5 minus x, and we have that equal to, the other cross product is 2 times the quantity, 2x plus 3. We then distribute, we get negative 15 plus 3x, so I would call that a danger zone right there, because a negative times a negative times a negative is a positive, right? So be very careful there. I often, if I see a wrong answer, that would be the first place I check as a teacher. 4x plus 6. Now I have x's on both sides, so I always suggest to deal with that fact first, that you have x's on both sides. So I'm going to subtract 3x on both sides. You could subtract 4x, but you can probably tell I'm a pretty positive person, so I like to stay positive, haha, right? So I have a positive 1x, and then I subtract 6, I minus 6 on both sides. Negative 21 equals x, so x equals negative 21. You can write it either way, but there's your answer. So cross multiplying is the way to solve these proportion or these rational equations. So now check these out. These are rational equations, but there's a little twist here. We have three terms. You see how it's not a fraction equals a fraction. Now, what is with this or thing? Well, I'm going to show you how to solve it two different ways. So the first way is I'm literally going to do the arithmetic over here. I'm going to add those up. I'm going to combine those first. So in order to add fractions, you have to have a common denominator. So 2 over 2 is the same thing as 1. So this is the same thing as x plus 2 over 2. When you add fractions, the denominator stays the same because you're just adding halves after all, so that makes sense. You would still have halves. Now you can cross multiply. So 2 times the quantity, 5 minus x equals 3 times the quantity, x plus 2. So we do the distributive property. 10 minus 2x equals 3x plus 6. We then add 2x. Notice how I'm showing all my work so that if I make a mistake, if my answer seems kind of weird, I can go back and I can check my answer. I subtract 6 on both sides. I get 4 equals 5x. I then divide by 5, and I get x equals 4/5. So you might be wondering, well, what is the other method? Well, you already saw me do it once earlier. Remember when I multiplied by the least common multiple? So we have the number 2, we have the denominator 1 there, and then the number 3. So what is the smallest number that is a multiple of 2 and 3? So this least common multiple. They all have a 6 as their first multiple. So I will multiply everything in this problem by 6 or 6 over 1. Now, 2 goes into 6 3 times. So on the first term, you're left with 3x over 1, right? It's gone. The denominator's gone. Plus 6, don't forget to multiply that 1 by 6, equals, and then on the right side, 3 goes into 6 2 times. So we're left with 2 times the quantity, 5 minus x. So this equation looks very different from, the one on the left side, but I have a feeling the answer will come out the same. Let's see. 10 minus 2x. I then add 2x on both sides. 5x plus 6 equals 10. I subtract 6. Oh my goodness, look what's going to happen. Divide by 5, and we get the same answer, x equals 4/5. So both ways are very acceptable. I would say if you can get the hang of multiplying by the least common multiple, it can shorten the problem and make it a little less confusing once you get the hang of it, but it is a little tricky at first, I'll give it that. A couple more rational equations where I put the x's in the bottom, but that shouldn't panic you because when you just do the cross products, you get 2x that way, and then the other direction, 2 times the quantity, 2 minus x. So see, it was no different. We still just do the cross product. So 4 minus 2x equals 2x. add 2x, we get 4x equals 4. We divide by 4, we get x equals 1. That wasn't so bad. And I know I'm going quickly, but I hopefully you're catching on. You're recalling how to do all these inverse operations as you solve these equations. So we'll do this cross product. 4 times the quantity x minus 1 equals, and then the other one, I always like to color code these. Hopefully that's helpful for you. 4x minus 4 equals, and on the right side I've got 6x plus 18. I can then subtract 4x. I always deal with the variables first. It's just how I roll here because I don't want to accidentally clear off one of the sides of the equation because it can create a problem or two for students. So subtract 18 on both sides. Negative 22 equals 2x. Divide by 2, we get x equals negative 11. So it came out to an integer answer. How cool is that? Okay, as we wrap up my review on solving equations, there's a couple special case equations that you should be aware of. Sometimes your teacher will give you a problem and you put a smile on your face and you're just so excited, you know how to do this. You jump right in, you start solving it, and then you say, oh, Mr. White says I should deal with the x's first. So I minus 6x, and I get negative 3. Wait, what happened? All of the variables just disappeared, right? Those added up to 0, and I have a false statement. This is not true, right? That's a false statement. So what do? That means the answer is no solution. No solution. There is no x. You could huff and puff all day. You're never going to find an x that can plug in here and cause the left side to be equal to the right side. This thing was doomed from the beginning. There is no answer, so no solution. All right, so let's look at this problem on the right. Now, I actually had a typo there. So if you downloaded my PDF of all these problems and you're following along, go ahead and correct that. I had to put an X right there. I just now realized that as I was doing the video. 2 minus 10x equals negative 10x plus 2. All right, again, you're going about your merry way. You add 10x on both sides because Mr. White said to deal with the x's. And all the x's disappeared. But this time I have a true statement. This is true. So we say all real numbers is our answer. Anything. Pick your favorite number and you can plug it in here and it'll work. 1,000,000, -1, 13 is my favorite number, 7, 17, whatever you want to plug in, the left side will equal the right side. Now, some teachers will give you the fancy schmancy symbol for all real numbers. It's the big capital R with the 2 vertical lines there. That means all real numbers. So it means we have no limitation on what can go into that. Solving literal equations or formulas for a specific variable is another skill that you practice this year. So they will always give you a formula like distance equals rate times time, d equals rt, and then they will tell you, they'll ask you, hey, solve it for a variable. Let's solve it for t. That means get t all by itself. So like I said earlier, if we want to get t all by itself, what do we have to get rid of? We have to get rid of the r. Now, how is it attached to the t? Is it multiplication, or can we subtract it off of there? Or how is it attached? It's attached by multiplication. So the way we get rid of that then, or undo it, is divide by r on both sides. And we show our work like this. So then the r's cancel. So time is distance divided by rate. That's what we mean by solving for a variable. Getting that variable all by itself and all the other letters and numbers get to the other side, but we have to use our order of operations in reverse. Now, as you know, when you're working with linear equations that I'll get to here later in this video, sometimes you have to solve for y. So here's where y is. So I need to get rid of this term. I need to get rid of the negative b, but I have to do it in the correct order. So if I subtract ax, that will cause it to pop up on the other side, right? Negative by equals c minus ax. And then how do we get rid of this negative b? Simply divide it, right? We can't add b because it's attached to the y by multiplication. I do see a lot of students try to add it. That's why I bring this up. So we divide by negative b, everything on the right side. So y is c minus ax all over negative b. Or you could even flip all the signs, and then you could write it might look a little nicer, ax minus c all over b. Or even, yet again here, we could write a over b x minus c over b. Lots of different ways to write the answer. All right, solving the volume of a cone. This is the volume of a cone that looks, something like this. Solving the volume of a cone for the height. All right, well, how do we get the 1/3 out of there? Remember working with fractions earlier? We don't divide by 1/3. We multiply both sides by 3. So we get 3v equals pi r squared h, because these 3's cancel. Then you take a deep breath and you say, okay, my goal is to get h by itself, so I need to get all this other stuff to the other side, and simply dividing it is enough to do that. See how we can do it all in one step. So h equals 3v over pi r squared. So these are called literal equations, or solving a formula or an equation for a specific variable. Okay, I wanted to throw a word problem or two into this. Problem solving, we have to read it carefully, identify the information that we've been given, and then come up with a plan. That's what problem solving is coming up with a plan to solve this. So let's read this. The fence around my rectangular backyard is 48 feet long. That means all the way around. So let's start drawing a picture. Here's my rectangular fence. All right, all the way around this is 48. If we add it all up, that's called perimeter. So the perimeter equals 48 feet. I like to summarize the information as much as I can, right? My yard is 3 feet longer than twice the width. Okay, so if this is the width, my yard is 3 feet longer than twice the width. So one side is W, and the other side is 2W plus 3, because that's 3 more than twice the width. All right, so this top here is W, and the left side is 2W plus 3, because this is a rectangle. So how do you find the perimeter? Don't you add up all the sides? So sure. So let's write an equation. We write 2 of these things, the 2W plus 3, plus 2W equals 48. See, we wrote an equation using the information given. So we had two sides, and then we had a bottom and a top that were both W, so that's where the 2W came from. Now we just solved the equation. 4W plus 6 plus 2W equals 48. That's 6W plus 6 equals 48. We then subtract 6 on both sides. 6W equals 42. We divide by 6. W equals 7. All right, so this side is 7. This side is 7 feet. Right? We should go ahead and put our units in there. And now we evaluate this expression. Remember, one of the very first slides we talked about today was expression. So 2W plus 3 is an expression. We will put the number W equals 7 in there. So 14 plus 3, that's 17. So 17 feet, so that means this side is 17 feet. So if we're going to answer the question, it's 17 feet by 7 feet. And those are the dimensions of the rectangular fence. So again, problem solving simply means reading carefully, identifying the information you're given. We were given perimeter, drawing a picture, and then coming up with a plan. My plan was that I can write a formula or an equation involving perimeter, and then I simply solved it. And then make sure you answer your question with your units and everything at the end. Inequalities, these are those greater than, less than symbols. So earlier, we talked about where we would get like one answer. X equals 3, that's a single answer. Well, maybe there are millions of answers, but not all real numbers, but only some of the numbers are answers. Well, then we might want to describe them with what we call an inequality. So this is read from left to right. X is less than or equal to 5. So all of the answers These are the answers over here, right? All the answers are under or equal to 5. So on our number line, we could put a closed circle right here and draw an arrow to the left to show a one-dimensional graph here. It's only in X, right? There is no Y on here. Where all the answers are. So the answers are in the red region there, and there aren't any answers up here, right? The answers start at 5, and then they go down from there. Now, I used a closed circle because 5 is one of the solutions. Like if I asked you, is x equal 5 a solution? Is 5 less than or equal to 5, question mark? It is. It's or, right? 5 is less than or equal to, either or. Now, on the right side here, we have x is greater than negative 2. We always read left to right. X is greater than negative 2. So we'll put an open circle this time because do you notice how it does not have the equal sign there this time? So that means we need to leave negative 2 out of consideration for solutions. So the answers are all the numbers, all the real numbers that are bigger than negative 2. Now, where are big numbers? They're to the right. They're to the right. So we draw our arrow to the right. So hopefully you're catching on. We've got an open circle when we do not have the equal as an option. We do a closed circle when we do have the equal as an option. So I get that question a lot, the open circle, closed circle. So I wanted to make sure I went over that on this slide. Okay, down below we have what's called compound inequalities, where several things are going on all at the same time. So this problem says that x is between negative 2 and 1. Notice the smaller number is written on the left. We have less than or equal to symbols, and then we have the big number on the right. So this is a between question where x is between those two things. So what we do is we put a closed circle here at negative 2, a closed circle at 1, and since the answers are all between, we draw a little line segment there between those two. All right, see how simple that is? That's called a compound inequality. All right, and then this last one has an or statement. Now, an or statement means either or, right? So let's draw the two graphs separately, and I'll do them in two different colors. So I'll do the first one in blue. X is less than negative 3, so that's an open circle because it does not have the equal. That's to the left. If x is under negative 3, that's to the left. And then the other one I'll do in red here. X is greater than or equal to 2 would be a closed circle here going to the right. All right, so if you are choosing an answer, if you're just picking an answer, would you not agree that you're either going to pick numbers that are up here or they're down here? You can't come up with an answer that's in both the red and the blue regions all at the same time. That would be the word and, but we've got the word or. There is no overlap on these graphs. So the solution is all the numbers down here, or we've got some more numbers up there, but we don't have any solutions that are in both regions at the same time. So that's called a compound inequality as well. All right, so we can solve linear inequalities much the same way that we solved equations. Like, for example, I want to know what x looks like, so I want to get x by itself. So I divide both sides by 2. X is less than or equal to 4. So then we would come over here, we'd put our closed circle at 4 and draw our arrow to the left, And that's the extent of the problem. Now on this next one, notice how I put the x on the right side. So that was just to make you think a little bit once we got to this last step. We divide by 3. We get x on one side and the number 2. So you could rewrite it if you want. X is less than 2. Just make sure that alligator is eating the bigger number here, which is the 2, right? The alligator is eating the 2 here, so the alligator needs to be eating the 2 there. So we're going to put an open circle at 2 and go to the left. All right, so that's an open circle pointing to the left, even though the little arrow-shaped thing was pointing to the right. You see how that can trick some students sometimes. They get into the habit of just looking at the arrow and thinking, well, this points to the right, so I'm going to draw my arrow to the right, and it's a greater than symbol, so it must go to the right. Well, no, the x is smaller than 2 is how you read that. All right, we've got a couple other things going on here, so let's just dig in and start graphing. So we subtract 5 on both sides. No big deal there. Negative 3x greater than or equal to 3. Now what do we do? What do we do? Do we add 3? No. You're probably getting tired of me asking that, but this is attached by multiplication, so we divide by a negative. Do you remember what that means from your class? When you divide an inequality by a negative, all the positives become negative, all the negatives become positive, so the entire world flips over by 180 degrees, which means this inequality has to be flipped around. So we have to flip the inequality around here when we're going to this next step. So we get x is less than or equal to negative 1. So we'd have a closed circle here pointing to the left. All right, and on this fourth question here, let's start with the distributive property, right? We have x's on both sides is how this problem is different, but good news is you already know how to do this. We deal with the x's first. We subtract 3x from both sides. I like to stay positive, so that's why I'm doing it that way. You could have subtracted 4x from both sides. That would be fine also. And then we subtract 1. Now, the way I chose to do it, of course, put the x on the right side. So you might want to rewrite it like this for your final answer so that your graph is more likely to be correct here, right? It's an arrow to the right. So an open circle, arrow to the right. Do you remember why it's an open circle? It's because this did not have the equal sign. Whenever it has the equal part, greater than or equal to, then we close that circle in when we're doing our graphs. All right, let's do a little bit of problem solving with linear inequality. So here's a word problem where sometimes the answer isn't just one thing. It's, lots of different possibilities. So let's read it carefully. A school is taking a field trip with 175 students and 10 adults. So it sounds like 185 people total. So let's write that down. Each bus can hold 30 per bus. All right. Determine the smallest number of buses possible. So we want the smallest number of buses possible. So every bus can hold 30. So 30 times the number of buses, we want that to be bigger than or equal to 185. Now, why bigger? Because we need to have capacity of at least 185, right? We need to have capacity for maybe 200. So if we divide by 30, I'm going to go to my handy dandy calculator here. 185 divided by 30 is 6.2. So the number of buses could be greater than or equal to 6.2. But let's think about this word problem, folks. Can we have 0.2 buses? No. Now, will 6 buses be enough? No, because the answers are everything above 6.2. So 6.3, 6.4, 6.5, and the first whole number would be 7. So 7 buses would be needed in order to get the kiddos and all the teachers to this field trip. And here's another classic problem. The sum of 2 consecutive even integers. What does consecutive mean? That means in a row. Like if you're counting consecutive numbers, you'd be 0, 1, 2, 3, 4, 5, 6. So if you're counting consecutive even numbers, that means 2, 4, 6, 8, 10. So what is the formula for that? Well, if you've got the number x, the next number would be x plus 2. That's what that means, okay? The sum of 2 consecutive even numbers, let's call them x and x plus 2, is at most 12. Now, what does the word sum mean? That means adding the 2 numbers up. Okay, so we've got the 2 numbers x and x plus 2, and if we sum them, if we add them up, the total that we get is at most 12. So that means we're under or equal to 12. If you think about it, it doesn't mean we're over 12. It means 12 is like the cap. It's the highest. It's the maximum. So our x plus 2 needs to be under or equal to 12 at all times. That's a statement of truth or an equation based on this problem that I just read. 2x plus 2 is always less than or equal to 12. We subtract 2 on both sides. 2x less than or equal to 10. We divide by 2. We get x is less than or equal to 5. So what does that mean? This means that x could be 5 or under, but remember, the x's are even numbers. They are even numbers. So x could be 4, 2, 0. You could even go into your negative numbers, right? But 4 would be the biggest that x could be. So really, I think in this word problem, maybe the best way to state the answer is all even numbers where x is less than or equal to 4. So 4, 2, 0, etc., etc. One of the big topics in algebra is the concept of a function. A function is a one-to-one rule between two variables. Now, what does that mean? Often, if you go in your algebra book, there will be like a picture of some machine, okay? And we put numbers in, and then numbers come out. So we put numbers in, and numbers go out. So maybe every time I put the number x equals 3 into this machine, maybe there's an output of 5, and we call that maybe a different variable. It's called the dependent variable, maybe y equals 5. So let's keep a table up here of our observations. So 3 goes in, 5 comes out. Well, let's try putting in a different number. Maybe 8 goes in and negative 1 comes out. So we'd have 8 and negative 1. And let's try one more combination. Maybe we put negative 5 into this machine and out pops 1. Now what if I went back and I put 8 in there again? What's going to happen? It's going to spit out negative 1. That's what's meant by one-to-one. Every time I put a certain number in, it's predictable based on some sort of formula. The same output happens every time. You can imagine if I put 8 in and then 2 came out the second time, that would be really confusing. You would feel like the machine was broken. All right, so a function is very predictable. Every time a certain number goes in, the same output happens. So inputs and outputs are combined together. So I have an example here. Y is always 3 more than twice x. So y is always 3 more than twice x. So you can imagine if I put, let's do a t-chart on that. If I put 1 in there, if I put it right there, what's 2 times 1? That's 2 plus 3 is 5. So we put 1 in there, we get 5 out. If I put 0 in, I get 3 out, right? 3 plus 2 times 0. If I put negative 1 in, I get 1 out. Every time. I could go back. You could keep watching this video over and over, and every time we put 0 in, we're going to get 3 out. So this is called a function because it's one-to-one, so every time a single input goes in, a predictable output happens. And it's that concept of a machine that just consistently does the same thing over and over. So functions have graphs, as you've learned this year in Algebra 1 so far. And these graphs represent all the input and output combinations that work in this function. So this point right here, it looks like it's 2 comma 4. So every time 2 goes into this function, we could call it f, 4 comes out. And I get that information off of the graph that I'm looking at right here. See, every time negative 2 goes in, it sure looks like 4 comes out. So those are ordered pair. By the way, negative 2 comma 4 is an ordered pair. It's x comma y. We always write that x coordinate first. So it's an input-output combination for this function f. Now on the right here, we have another graph, and this is not a function. This is not a function because it fails the vertical line test. Let me show you what I'm talking about here. You see this dot right here, and this dot right here, and this dot right here. You see how they're all lined up vertically? They're on top of each other. That's how you can spot when something is not a function. Because, check this out. If I put 3 in, I have 3 options that might come out of this relation, it's called. It's a relationship. It's not a function, so I can't use the word function with this. So it looks like, if I go over 3, it looks like up 3, right? So that's one option, or maybe up about 4, and then up, let's count this carefully. If we go over 3, up, how many is that? That's 3, 6, 8. 3, 8 is another possibility. This thing fails the vertical line test because there are points on top of each other. So that indicates that we might get multiple outputs, and that's a problem. Whereas the graph on the left, if I draw a vertical line, it only hits once. If I draw a vertical line anywhere, it only hits once. That's how you can spot graphically if you've got a function on your hands or not. It's called the vertical line test. So these x values are not allowed to repeat and get different outputs. So that's how you can spot. If you're just given some points, you can spot whether it's a function. So, for example, is this a function, question mark? If I write 1, 3, and then 1, 5, and then 2, 8, is that a function? The answer is no, because 1 goes in, we get 3 out. 1 goes in again, we get a different output out. So the x's are not allowed to repeat and get different outputs. Okay, so this would be no, this is not a function. We have function notation. So this is pronounced f of x. F of x. That means a function f composed or made up of the independent variable x. So this is where we put our inputs in. Okay, so the x tells you where we put things in. So f of x means we have a function, first of all, it would pass the vertical line test, and this is where we would put our values in. So this is pronounced g of x. This is pronounced h of x. So then, down below, when I ask you to find or evaluate f of 1, what does that mean? That means you're going to put x equals 1 into the function. So the function f is x plus 3. So we're going to use that function. So we put 1 plus 3, that equals 4. So we would say f of 1 equals 4. And by the way, as an ordered pair, that means that 1, 4 is on the graph of f. Now off to the right, I've got g of negative 1. Well, see, the advantage of this notation is you know instantly which function to look at. You know we're talking about the g function this time. So we do 2 times the input minus 1, because remember, this is where we put numbers in, right there. So what are we putting in? We're putting negative 1. So that's negative 2 minus 1, that's negative 3. So once again, the point negative 1, comma, negative 3 would be on the graph of the function g. Now the function h is a fun one. It squares the input. You see how we put numbers in here. Whatever the x value is, we put it in. So this would be 2 squared, and that's 4. Now what about h of negative 3? Be careful here, folks. Remember what I talked about earlier? Negative 3 squared, if you type that in the calculator, it's going to say negative 9. But yet we are squaring, remember our x is negative 3, so you have to put parentheses. We're squaring the negative. We get positive 9 this time as the answer. All right, and on the next one, I like to color code these. So f of g of 3. You see how it's like Russian nesting dolls here. We've got a function inside a function. So you start from the inside and you find the answer for g of 3. So you come up here and you plug 3 into g. That would be 6 minus 1, which is 5, right? And then in part 2, you then take that output and you put it into the f function, and what pops out now? We get 8. You are literally connecting two machines together. So we started with the g machine, we put 3 into the g machine right here, and out popped 5. We then took that output and immediately put it in to the f function. 5 plus 3 is 8. Now down below, I'm putting one function in the other function entirely. Remember what the h function does? This is called a composition of two functions. The h function over here is the square function. What are we putting in? We're putting g in. And look at this. I'm even making this really tricky. I need to put t in for x. So there's your answer. I just composed two functions, it's called, where you nest one function inside the other, and I even replaced the x with a t because that's what it said to do. It said to write g of t. So this would be my answer for h of g of t. function notation. You're going to be using this all the way to AP Calculus and beyond when you're a math major in college, right? We can also read values of function notation off of graphs. So here we have a crazy graph down below. I don't even know what that function is, but it doesn't matter. We can read this information off the graph. F of 2 is. So what that means is you go over 2 and you figure out where the graph exists. So if I go over 2, I'm right here, folks. I'm right here. This is the point 2, 5. So that means f of 2 is 5. I can read that off of the graph. What about negative 1? Well, I go back 1 and I go up. That would be 2. What about 0? I go over 0, I go up 3. That's what the graph says. See, a graph is a picture that shows you all the xy combinations that work. F of 7, let's go. There's 3, 7 would be right here. That would be a 1. Okay, for what values of x is f of x equal 1? See, now this is tricky, folks. This is where the y value is 1, and we're asking what x values satisfy that. Well, we have to go to y equals 1 and imagine drawing a horizontal line here. That's y equals 1. And we have a point right here, we have a point right here, we have a point right here, and a point right here. So there are 4 x values. So for example, you might say, let's see, 1, 2, 3, 4, 5, negative 5.7, right? Negative 5.7 looks like one of them because this point right here. 6, 7, 8, 9. Maybe negative 9 is another one. Looks like 4 is one of the x values, and then also 7. Right? You see how we did that? We used the line y equals 1 to find the x values that could generate the output of 1. Because that's, again, what you're asking is you're saying, what we've got this machine, f, when does it output 1? It would output it at those 4 different values. So if we have a graph that maybe starts here and goes here next, and then here next, and then here next, how is this changing? That's the idea of a rate of change of a function. And the way we describe this is how far up and over is this going from point to point. Now, this particular graph is constantly going up 1 over 2, up 1 over 2, up 1 over 2, up 1 over 2. So given 2 points, a comma f of a, remember that's just the y component, so this is just x and y, and then the second point is b comma f of b, so that's a second point with an x-y combination. So the way you find the average rate of change between any 2 points, it could be these two or it could be these two, it really doesn't matter. What you do is you subtract the x's. What you do is you subtract the y's, and then you divide that by the x's subtracted, just like that. So f of a minus f of b, so that's the y value subtracted, over the x value subtracted. And again, that could be any 2 points on a graph, and they actually don't even have to line up to form a line. We could have a curve, maybe like this, and here's the graph of the function, and maybe we want to know how was the function changing from here to here. Well, we are going to find the difference of the y's and the difference of the x's, and we're going to subtract them. So we use the symbol, the triangle symbol, it's called delta, for the word change in math. So that's the change in y over the change in x is exactly what's happening in this formula. We subtract the y's over subtract the x's. That's how you find the average rate of change between 2 points on a graph from a function. Well, now I'm asking you for the average rate of change of a function given a table of information, and I'm saying between x equals 4 and x equals 6. So if we circle it down here, you see it's right here. Here's 4 to 6. So let's see what the y values are doing on this function h of x. So the average rate of change would be the y value subtracted 6 minus 3 all divided by 4 minus 6. This is the average rate of change. And this would be 3 over negative 2. So it looks like it's going down 3 over 2, but only necessarily between 4 and 6. From 4 to 6, that was the average rate of change on that previous slide. Remember, the rate of change can be different in different locations, which is why I have this second problem on here. This problem says, okay, now find the average rate of change between 0, x equals 0, and x equals 4. So we're going to subtract the y's, so the average rate of change will be 10 minus 6, all divided by 0 minus 4. So that's 4 over negative 4, which is negative 1. So as you can see, we got different values based on using two different points. So it appears that these do not line up. They form some sort of a curve instead of a line. So now let's spend some time talking about domain and range, because this is a really important topic that will be around all the way through your senior year. Now, domain describes what you are putting into a function or what is allowed to go into the function. So if you see this function, this x squared, we could ask, what are we allowed to input into this? Well, we're actually allowed to put anything we want in here because you can always square something, right? You can square positives, you can square negatives, you can even square 0. So we would say the domain on this is all real numbers. However, let's think about the t-chart on this. When we're plugging in values for x, we might plug in 0, we might plug in 1, 2, and we get 0, 1, 4. And then what about negative 1? We get 1, and then we get 4 when we plug negative 2 in. We're always getting positives. So what does the range look like? Because the range is the outputs of the function. So as we're looking at the table, we can observe what the outputs are. Do you see how they're always positive? There's 0. We did get 0 on this machine. It spit out 0 at one point, but all of the outputs are 0 and higher. So what we would say is that the range, the outputs of this function are y is greater than or equal to 0 at all times. Now, what about the function on the right here, this function g of x? Well, this is called a linear function, as we're going to see here in a moment. What are we allowed to put into this thing? Well, once again, we are allowed to put anything we want in here. Domain is about inputs, so domain would be all real numbers once again. Now, what numbers come out of this thing? Well, there is no squaring, so it's not going to make everything positive. So this function, as we'll see when we graph these here in a little bit, are also all real numbers when it comes to the outputs. If we did our t-chart, I'm not going to take time to do this, but with g of x, you will eventually see all real numbers here. Like we could get it to spit out 1,000,000. We could get it to spit out negative 1,000,000. We could get it to spit out 0 if we wanted. We just have to pick the right input. But on this side of the graph, we could never, ever get this function to spit out a negative. I can't come up with an x that when you square it, you will get a negative 5, for example, or a negative 9. It's just not going to happen unless you're working with imaginary numbers, which you'll look at in Algebra 2. All right, so remember, domain is input, and input is x values, whereas range is output, or y values. So I've explained a bit how to think about this numerically as well as sort of looking at the function, but what about the graph? It's really easy once you realize how to do this. The domain is x values, right? That's this axis here. So all you have to do is ask yourself, how far left and how far right does this graph go? Just look at the x information, these numbers right here. How far left and how far right does the graph go? So this one would have a domain from negative 3, right? And x is bigger than that. You see how, and I don't put the equal sign because this is an open circle here. And we have a closed circle here, so we go as high as 1. So I wrote a compound inequality. Now, if you're using interval notation, maybe your teacher taught you interval notation, negative 3, comma 1 with a bracket is how you would write that. Let's go to this function here. You see, how far left does this go? How far left does it go? It goes as far as negative 3. You see that? We're looking at x values. I'm only looking at domain right now. So it goes as far left as negative 3, and then the x's go as high as 2, but never quite get there because once again we have an open circle on at the end of that function as far as the far right. All right, let's backtrack now and go back to this graph. Let's talk about the range of this now. Remember, range is y values, so it's really simple. Again, now you look at the up and down, the y-axis, and you say, how low and how high does this graph go? How low, how high does it go? Because that's range. I think it goes as low as -4. You see that right here? It's as low as -4 and also over here. So let's put that in. -4 less than or equal to y less than, and how high does it go? Well, it looks like it touches the x-axis here. It looks like it does touch it there. So I am going to put an equal sign under here and say y equals 0. That would be the x-axis. It's how high and how low the graph was, and it was from 0 to -4. All right, the graph on the right over here, what's the range? What is it? It would be y is between what and what? Well, it's above -5. I see that right here. You see how this is above -5. And you don't go to the end. That's a common mistake, is go to the end. Just ask yourself, how high does it go? Ever, 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 it goes as high as 4. So that would be the range then. The range is that. The domain was that. All right, I got a couple other examples here. So let's just talk through this. The domain here would be from -2 to 3, without 3, right? And then the range would be as low as -5, as high as 4. What about this graph here? Well, this has arrows on the end. This looks a little bit like maybe an x to the third graph. So what does that mean? How far left and how far right does this go? It goes forever. It's going to keep going because this will just keep going this way. This will keep going this way. And also, not only up and down, but left and right. So this function here, the domain is all real numbers, and the range is all real numbers as well. Now, this is an absolute value function. It has this corner down here where we have two lines sort of going away from each other, starting somewhere. So what is the domain on this? What is allowed to go in to the function, that absolute value function that we don't see here? But we know from the graph that the graph goes forever and ever in either direction on the x-axis. So we would say all real numbers. However, what about the range? It's not all real numbers. How low does it go? It goes as low as the x-axis and then goes forever. So we would say the range is y is greater than or equal to 0. So it goes from 0 all the way up to infinity. All right, as we're getting ready to graph lines, we need to talk about proportionality and those relationships. So if the division of two variables is always some constant, so for example, maybe y is to x as 3 is to 1. You see how y is always 3 times bigger than x. So if y is 6, x would be 2, for example. This is called proportionality. So let's read this next problem here. It says if 6 potatoes cost $2, so 6 potatoes cost $2. See how that's a proportion? That's 6 is to 2. How much would 10 potatoes cost? We put an x here. Now this is called a proportion, and do you remember how to solve proportions? You cross multiply. So remember how we did that earlier when we were solving equations. So 10 times 2 is going to equal 6 times x. So this would be 20 divided by 6 is the cost of that. All right, so that would be $3.33. $3.33 is how much 10 potatoes would cost. Now on the graph, you can see how we could say, okay, 0 potatoes cost $0, right? So if we go to 6 potatoes, our cost is $2. If we go up 6 more, there's 4, there's 6, we would have to go over 2 more dollars. Okay, this is dollars down here, and this is potatoes over here. All right, and then if I go up 6 more, that'd be right here. I have to go over $2, and you see my line here. It's the line that shows how much it would cost to buy different numbers of potatoes. So here's that 10 potato line. If we go right over here, and go down like this. Remember, I said it was going to be $3.33. So between $3 and $4, which is exactly where that line hits right there. So an example of a proportional relationship would be distance equals rate times time. Because if you divide by time on both sides, you could see that every time you take the distance divided by time, it's going to be some rate. So if you're traveling at some constant rate, then the distance is going to be very predictable how long you're going to go, right? John has traveled 150 miles in 3 hours, so we would write 150 is to 3. Okay, if he continues at that rate, how many more miles could he travel in 2 hours? So what we do is we do a 2 here, and we put an x up here. So 150 is to 3 as x is to 2. Cross multiply, and you get 2 times 150 is 300 equals 3x. It looks like he could go another 100 miles since he's traveling apparently 50 miles an hour, right? If we find, it's called the unit rate that I'll talk about here in a moment, but he is going 50 miles every 1 hour, right? You could take and divide that out, and that's called the unit rate that we'll see here in a moment. So if we start here, and then he went for 2 hours, right? He went 100 miles, so that would be right here. So, and then everything in between. So as he was traveling away from home, after 1 hour, he went his 50, and then after 2 hours, he went his 100. Okay, so as I mentioned on the last slide, we have a concept of a unit rate. So convert into unit rates is really easy, folks. All you do is actually do the division. So 30 feet in 3 seconds. We want to know how many feet in 1 second. Well, that's pretty easy. If you divide it out, it's 10 feet per second. 10 feet per second. This would be called the unit rate. Now on this next one, we have 75 pounds per 5 boxes. Well, how many pounds per 1 box then would that be? Would that be 15 pounds per box? Right, the unit rate is used a lot, at least I use it a lot at the grocery store because I want to figure out which package is the cheapest. And sometimes they put the small ones on sale, and you actually want to buy a bunch of small packages instead of the one big package because you will actually save money by doing it that way. And if you figure out the unit rate, you can compare the two different sizes very easily. Now that we talked about unit rates, we can talk about unit conversions. And this was a topic that always gave me trouble in high school chemistry class. And it wasn't until I realized that we just let the units drive the problem that I began to have some success at this. So let me share the technique that I'm talking about. So we are going to do some conversion. So it says, how many centimeters are in 1 foot? If there are 2.54 centimeters in every inch. Now, of course, there's one other fact that we're going to need in this problem is how many inches in a foot. So you probably have that one memorized, and that's why I didn't put it in here. But there are 12 inches in 1 foot. Now, before you jump in and trying to figure this out mentally, let me show you how to do this with very little thought. So what you do is on the left side, you put your given. The given is that we are starting with 1 foot, okay? And then on the right side, we put our goal over here. Our goal is to figure out what unit do we want to figure out. We want centimeters over here, okay? Now in the middle, we're going to put some parentheses. These are called conversion factors. We don't really know how many we'll need, so we'll put a couple there for now. We'll put a fraction bar because each one is going to be a fraction. It's going to be a unit conversion on its own. Now, I had a fellow teacher once, a science teacher, who called these the bones. So we put the bones in here, and then we're going to put the meat on the bones here next. All right, so let the units drive the problem. What do I mean by that? What I mean is we want to get rid of feet. So in this fraction here, where would feet need to be? We want the units to cancel, so we're going to have feet on the bottom. Now, what do we know about feet that gets us one step closer to centimeters, which is the goal? We know how many inches are in a foot. So we put inches up there. Notice how I put the units in first, and then I put the numbers in. So there's 12 inches in 1 foot, and I would suggest you say it out loud so that you get the 12 in the correct place. 12 inches is 1 foot. Now, I don't want inches in my answer, right? I don't want inches. This is the only thing that's not crossed out so far. We want centimeters. So where will inches need to go on this next fraction if we want to cancel that? We let the units drive the problem. The inches have to be on the bottom. That way they'll cancel. Now, do we know anything about inches and centimeters? Yes, it was given in the problem right here. 2.54 centimeters is 1 inch. All right, so everything is crossed off except for centimeters, which is exactly what we want. Again, we're letting the units drive the problem here. We now multiply the top of the fraction, multiply the bottom of the fraction, and then divide, right? You multiply straight across when you're doing fractions. Now, the denominator is all 1 in this particular example. That's not always the case, but it is in this one. So you would take 12 times 2.54 and divide by 1. So that equals 30.48 centimeters, and that's our answer. So we did a unit conversion, and we let the units drive the problem, making sure that they canceled along the way. Now, I've got an entire video devoted to this. You might want to check that out on my channel because I know this can be confusing. As I said in high school chemistry class, I struggled with this, so I know it's difficult. But if you just fill the units in first, it really helps tremendously, and you don't have to memorize formulas or try to figure out, wait, do I multiply or divide by 12? Let me think about it. I didn't have to think about it at all. I just made sure that the units canceled, and then I knew to multiply by 12. So let's look at another example of this. Since I know this is tricky, I wanted to put a second example in here. Let the units drive the problem again. This time we're going to convert 60 miles per hour to feet per second, because in our physics or science class, sometimes we see feet per second, and we're wondering, okay, 60 miles an hour, that's how fast a car is driving on the highway. How many feet per second is that? All right, let's figure it out. We start with our given on the left side. 60 miles is our given, and that's on the top, by the way. It's over 1. We're going to have some bones in here. We don't know how many we need, so I'll put lots, right? I'll put way too many, probably. Let's see, I don't know. Equals, and I want feet per second. So by the way, the given was miles per hour, so I really should have had the unit hour on the bottom. All right, so let's let the units drive the problem. We want to cancel miles, so where does it go on this next one? It goes on the bottom. Now, what do we know about miles? Well, we know how many feet are in a mile. There's 5280 feet in a mile, in 1 mile. That's a fact. You might want to memorize that, but you could always look that up. 5280 feet in 1 mile. So I'm going to sneak a 5280 right in here. 5280 is 1 mile. And now the miles have canceled. Now look at this. We wanted to get to feet, and we've successfully gotten there. So that's good so far. Now let's focus on getting the seconds converted. So we'll start with hours. So hours are on the bottom. So in this next fraction, where does it need to go? It needs to go on the top. So I'll let the units drive the problem. I put the units in first. So hour goes there. What do we know about hours? Well, we know how many minutes are in an hour, don't we? There are 60 minutes in 1 hour. So 1 hour is 60 minutes. Again, remember I said say it out loud, so make sure you get the 60 in the right place. And then on the next one, we want, by the way, the hours are gone. We want minutes to cancel again. So minutes to seconds. All right, how many minutes in a second, or how many seconds in a minute? It's 1 minute is 60 seconds. Okay, so we have now arrived at our seconds right here. So we will not need this last set of parentheses. So I'll go ahead and erase it so it's not in the way. All right, so we multiply straight across the top and then divide by the bottom. So it's going to be 60 times 5280 divided by, and in parentheses on your calculator, you would type 60 times 60. And that equals 88 feet per second. All right, so we converted miles per hour to feet per second. So 88 feet per second is pretty darn fast. It's 60 miles per hour. All right, so in your algebra class, you then talked about how to graph a linear function using slope-intercept form. So slope-intercept form is y equals mx plus b, or we could use this function notation because f of x is the same thing as y after all. But either way, it's mx plus b, where m is the slope of the line. Okay, slope of the line, so that's the change in y2 minus y1, all over the change in x, x2 minus x1. So we'll figure that out. And then the b value, that is the y-intercept of the line. So that is where the line hits the y-axis. So that's kind of like a freebie point when you're in y equals mx plus b form. So let's graph this function here. F of x equals 2/3 x plus 1. Now don't freak out because it has a fraction in it, because a fraction is simply slope in this problem. So our y-intercept is your b value, which is plus 1. So you start with that. That's step number 1. Step number 2 is to use the slope is 2/3. Now that's rise over run. Rise over run. So I always say go up or down and then go right if you want to go be right. So this is a positive slope. So I start on the purple dot here and I go up 2 because the slope is positive, and always go right if you want to be right. Just trust me. So our second dot is right here, and then you can keep doing that up 2 to the right 3. Or if you want to backtrack, then you go the opposite direction, which would be here, right? They're all going to line up. So we get our beautiful line here. Y equals 2/3 x plus 1. F of x equals 2/3 x plus 1. Again, on my channel, I've got some videos talking about how to graph this form, because I know this is super important for both Algebra 1 and Algebra 2. So make sure you're good at it. Speaking of which, we have another example lined up, and this one has a negative slope. So I wanted to be sure to go through 2 examples, one with a positive slope and one with a negative. All right, so the b value here is 5. And what does b mean again? That's your y-intercept. So you go up 5 and you put a dot right there. Now, the slope is negative 4/3. So the slope, we use the letter m for slope. Negative 4/3 is the slope. So that's your rise and your run. So you're going to go down and to the right. Always go right if you want to be right. So the slope, this is going to be downhill this time. So down 4 from our blue dot, down 4 to the right 3 gets me right here. Okay. And we draw our line like this, and there it is. That's y equals negative 4/3 x plus 3. You see how it's downhill? Like if you were skiing down here, you would be going downhill. So that's a negative slope line. Uphill is positive slope line. Another example of graphing y equals mx plus b, but look here, it is not in slope-intercept form, but we have an algebra toolbox where we can solve for y, right? We can solve for y like we did earlier when we were doing literal equations. We had to get y by itself. That's what we're going to do here. So let's subtract 2x on both sides. 3y equals negative 2x plus 3. We then divide everything by 3. Notice how I'm going to use small fractions on everything rather than doing a big fraction bar on the right, because 3 divided by 3 is 1. Negative 2/3 x plus 1. Look at that. That's in mx plus b form, slope-intercept form. So we go up 1, put a dot, right? That comes from that b value. Up 1, put a dot, and then are we going to go up and to the right or down and to the right? Well, it's a negative slope, so you better go down and to the right if you want to be right. So negative 2, and then always go right if you want to be right. This is going to be a downhill line, so you can plot lots of dots that all line up. That's the line y equals negative 2/3 x plus 1, but it's also in this form, 2x plus 3y, which, by the way, that's called standard. Standard form is what this is here when you have ax plus by equals c. All right, we're in the home stretch here, folks. Let's write the linear function shown. So you see how I have a nice blue line on that graph, and we're going to write the function. So f of x equals something x plus or minus something. So we're going to put the slope here, and we're going to put the y-intercept here. You can just plug them in. I like to call it a pluggable formula. So what is the y-intercept on this thing? Where does it hit the y-axis? Okay, we're not looking over here. Don't look over there. The y-intercept is on the y-axis, of course. That's pretty obvious, right? Up 3. So we put a plus 3 at the end here. Now, what is the angle of this line? Now, we don't use angles in algebra. We use slope. So give me a rise over run fraction. So I've got one dot. Let's find another dot. Well, I see one here. I see one here. I see one here. I tried to make sure this line lined up well with, a couple different dots, and you can see that that does. That sure looks like it goes up 1 to the right 2 every time. So that's the ratio. Okay, that's the proportionality of this line. It's a 1 to 2 relationship starting at 3. So we put that slope in there, and we have just written the function described by the line, or we've just written the function that would generate the line if we were to graph it. Now, it wouldn't be fair to me to not talk about two different special cases. The graphs of a horizontal line, that's the red one, and then a vertical line, that's the blue line, are special equations. So the way I think about, let's start with the red line, the horizontal. That sure looks like it's always 5 high, right? And the height is a y value. So this red equation is y is always 5. It doesn't matter what x is. Here, here, here. X can be anything, but y is always 5. So this, for example, is negative 3, 5. Over here, this is 6, 5. You see how y is always 5 on the red line. Now tell me about the blue line. Where is the blue line? Well, it sure looks like all the points have something in common, and it is that we go over to x equals 3 and we stay there. So that's the equation of the blue line, because all the points have an x-coordinate of 3. So the one I highlighted there is 3, 8. We've got 3, 6, and so on. So the equation in the xy world for a vertical line is just x equals something. And then a horizontal line on this xy universe here, the Cartesian grid here, is y equals 5. So we've looked at y equals mx plus b, and that's really handy for both creating equations and also graphing. But there's another form that's really helpful, point-slope form. This is if you're given a point. So if you're given a point, x1, y1, and then you have the slope, you can plug these values into the equation. So the x value goes there, and the y value goes right in there. So you need to have those three things. You need to have a point on the line, so you have an x and a y value, and then the third thing is a slope. So write the linear function in slope-intercept form that passes through these points. Well, I said we needed a point. We actually have 2 points, so we have extra information there. We have 2 points, so either one we can use, but do we have the slope? No. So I'm glad I put this problem on here, because I probably should have put it earlier in the presentation, is calculating the slope from 2 points. So I had the formula earlier, y2 minus y1 all over x2 minus x1. That's the formula for slope. So you subtract the y's, 4 minus negative 2, all over 2 minus negative 1. We did this calculation when we were finding the rate of change on that table. Do you remember how we subtracted the y's, we subtracted the x's, and we made a fraction? That's what we're doing here. We got 6 over 3. That's a slope of 2 over 1, or just 2 is a great way to write that. So the slope is 2, and the points are given. So let's plug into our formula. Y minus y1 equals m times the quantity x minus x1. So everything I've written in black is just part of the formula. We have 3 spots where we need to fill in our blanks. Okay, y minus, which one would you like to use? Let's use this point here. Okay, so the y is the 4. So in goes, I guess I should do this with a color. There we go. Y minus 4, x minus 2. And again, those came from this point right here because the x value of 2 is paired with the y equals 4. Now, what is the slope? The slope is 2. Okay, that came from our calculation over here. Let's read the problem again. Are we done? We've written an xy function, but we have not written it in slope-intercept form like it requested. So we better go ahead and do that. So what we do is we do the distributive property here. We get 2x minus 4 equals y minus 4. You then add 4 on both sides. Oh, this problem is neat. Y equals 2x plus 0. So this is an example of a proportional, a direct relationship here where y is always 2 times bigger than x. Y equals 2x plus 0. So if you were asked to graph this, the y-intercept would be at 0. And then you would go up 2 over 1 and graph it. There's the graph. Again, the slope was 2. We had to calculate it, and we used point slope to easily plug in and get our equation on our paper so we could then convert to our y equals mx plus b form. Hang tight, everyone. We are super close. So absolute value and those absolute value equations might be something that you covered in your Algebra 1 class. So the absolute value is where you don't care about the sign. So the absolute value of 5 is 5. The absolute value of negative 5 is also 5 because I literally don't care about the sign. I just want to know how far away is that dot from 0 on the number line. I don't care plus or minus. I just want to know what is the spread here. It's 5 away from 0. So it's also a grouping symbol. So inside we have 2 here. The absolute value of 2 is 2. And on the fourth problem, we have 2 minus 4 inside the absolute value symbol, which is these goalposts. The absolute value of negative 2 is positive 2. So in the end, you throw away the sign. Now solve for x equals 4. So when you solve an equation, you're trying to figure out what works. Well, x equals 4 is a solution since the absolute value of 4 equals 4, right? But there's a second solution. X equals negative 4 is also an answer since the absolute value of negative 4 also equals 4. You see how solutions are values that work when you plug them in, and we found 2 answers that work here. So solving this next equation, the absolute value of x plus 3 equals 1. You want to consider 2 options, and the 2 options are this stuff inside, this x plus 3 could turn out to be 1 and we'd be good. Or that stuff inside, x plus 3, don't change that to a minus, okay, x plus 3 could come out to be negative 1, and then we'd have the absolute value of negative 1, which is 1, so that would work also. So you need to branch this out into 2 options. Okay, sometimes I do like an upside down V there to show that. Subtract 3 on both sides. We get x equals negative 2, and then subtract 3 over here. Notice we're not going to get positive 2 as our other answer. We got 2 negatives. How crazy is that? It is possible to get 2 negative answers to positive numbers, or maybe one of each. It's entirely possible on these things. Okay, here's 2 more examples of absolute value equations. They're really easy once you get the hang of it. You need to branch them off. So 4x minus 1 equals 3, or 4x minus 1 equals negative 3. You then just solve like we did earlier in the course, and you get your 2 answers. So x equals 1. Or over here, if we add 1 on both sides, we get 4x equals -2. We divide by 4, we get x equals -1/2. So we got two different options. Now take a look at this next example. You might be thinking, why is he doing another one? It seems like I've got it, right? But look at this. The right side is negative. So let me ask you this. What could be inside that would ever be negative after you take the absolute value? Right? This thing right inside here, the 6x plus 1, I'm just summarizing it as saying, let's call that a variable y. The absolute value of what would be -5? Nothing. So the answer is no solution. No solution here because that right side is negative. So absolute value functions are kind of interesting. What happens is when x is positive, the line matches y equals x for x is greater than or equal to 0. So it's not going to change at all. On the right side, it has a slope of 1 and it goes through y equals 0. But on the other side, when x is negative, what's going to happen is it's going to turn it positive. So we get the line y equals -x on the left side is what this will look like. So that's down 1 over 1. So these are V-shape graphs. They have what's called a corner here at the bottom. So all absolute value functions are going to have a corner like that. Let's do the second function. We can use transformations, right, to actually solve this. So this down 2, it moves it down 2, and then the transformation here is where it moves it to the left by 3. So it's going to be right here. And then this thing is going to be a slope of 2 instead of a slope of 1. So it's going to be up 2 over 1 or up 2 back 1. So it's a more narrow V-shaped graph. So there's the graph here of shown there, and I use transformations to solve that. Here's our last slide, folks. Linear inequalities. Inequalities are where you have millions of solutions that satisfy a statement. Now, answers to linear inequalities are points, and we're going to describe them with a shaded region. So what you do is you graph the boundary line first, boundary line. I've got a really good video I was very proud of on how to graph these linear inequalities, so you can search for that on my channel as well, and I'll link it down below. But so the boundary line, you start by going up 1, put a dot, and then you go up 3 over 1 because the slope is 3 on that, right? You've gotten good at graphing y equals mx plus b. Now, the y value always has to be smaller than this expression. Whenever the linear inequality is solved for y, you can use a nifty trick, and that is, where are y's smaller than the line? Y values are really small down below, so we shade under the line here. So we shade down here. Okay, so what this means is that all of these points that are in the shaded regions are called solutions, and any point over here is not going to be a solution. So I sometimes say the frowny face is over here and the smiley faces, the party is going on over here. This is where the solution is. So is 2, -2 a solution? 2, -2 is right here. Yes, it is, okay? Now let's look at the next one. Notice it does not have the equal sign here. So when we draw the line, I'm going to go up 3, put a dot, down 2 to the right 5. We draw a dotted line to show that the line is not part of the solution. So we do a dotted boundary line, and that's because it does not have the equal sign there. Now, I didn't a greater than this time, so when are the y's really big? That is when we are above the line. So is 2, -2 a solution this time? It's down here. No, it's not. The frowny faces are down here, so that is not a solution. Okay, I prepped you for a whole bunch of stuff from semester 1 of Algebra 1. I really appreciate you sticking through the whole video, and be sure to like and subscribe here, and also check out all the other linked videos down below, as well as search my channel, and you're going to find all kinds of algebra stuff. All right, good luck on your test. I certainly wish you well.